Okay, so I have a heat sink at 353K, so it's like ADC, and it's absorbing heat from copper as copper cools down from 100 degrees Celsius, 200 degrees Celsius to 100 degrees Celsius. And we want to determine the change in entropy for the copper, as well as the entropy generation for the whole process. And we want to know whether the process is reversible or not. So first thing we got to do is make the assumptions. And the assumptions are twofold. One, pretty good assumption because it looks like it. It's a closed system. And two, copper, seeing that it is a solid, is incompressible. Okay, it's not a gas. So we're going to use the incompressible assumption for the second law. Okay, so let me sketch out what's going on here. We have a heat sink. So it's the environment, and dotted is our system. And inside here, there's copper. And what's going to happen is basically just heat is going to be interfacing across that dotted line into the surroundings. The surroundings here inside the big solid box is at 80 degrees Celsius, 353K. And copper changes its temperature from T1 of 473K to T2 at 373K. Okay, and we know it's CP. We're going to also make the assumption that CP is T invariant. Okay, so the entropy change for an incompressible substance for copper, we're going to say it's incompressible. So to get the entropy change, I'll remind you, it's the integral, okay, of C dt over T from T1 to T2. Okay, we're going to assume that the C is equal to CP because it's incompressible. All the specific heats will be equal. So it's going to come out of the integral. And we're going to basically get MCU times CP of copper times the ln of T2 over T1. That's going to give us that. Okay, so what we're going to do is we're going to put T2 is 373. T1 is 473. CP is 0.4 joules per gram per Kelvin for copper. And the mass for copper is 3,000 grams. So when you put all of this together, you get negative 285 joules per Kelvin. That gives us the delta S for the copper. Great. All right. So now we want to know the entropy generation for this process. Okay, so for this process, we're gonna write the second law, the entropy balance for it. Delta S for the process for the system is going to be Q for the system divided by T for the reservoir, Q for the system, Q for the process or whatever, plus this for the process, for the overall process. Okay. So what we're going to do is we need to figure out Q first. We don't have Q. So we have delta S, that's fine. We have the T of the reservoir, that's 353K. And so in order for us to get this, we need to get Q. Okay, if we look at the first law, and we already established this is a closed system. First law, closed system. We know that delta U is equal to Q minus W. Since there is no work, because this is incompressible. And work is PDV, and there's no change in volume. Then we get that Q is equal to mCV delta T, okay? And again, because incompressible, CV is equal to CP, so we can just use Q is equal to mCP delta T. So we know that Q is mCP delta T, which we know is 3,000 grams times the CP for copper over here is 0.4 joules per gram Kelvin times the change in temperature, which it goes from 473 to 373, so it's 373 minus 473 K. And we get that Q is negative 120,000 joules. Okay, so lastly now, what we need to do is use that information directly here. So delta S for the system, we just calculated as negative 285 joules per Kelvin. So I'm going to put that in directly over here. This is negative 285 joules per Kelvin. Q is negative 120,000 joules. The temperature is that of the reservoir, which is at 353 K, plus the entropy generation, and therefore we get that the entropy generation is 24.3 joules per Kelvin. Since this is greater than 0, this is irreversible.